Alright, in this let's look at vector components, and many times when we're working with vectors, it is actually easier to break a vector up into its component and then use those components to start to work with those vectors. Now, components really are is it's another way of including information about direction in our vector or in our information about a vector. If we have an angle and a magnitude in two-dimensional space, we need two components to describe what's going to happen in two-dimensional space. A lot of times I would call this the x component and the y component. How far left and right, east and west does the vector go, and how far up or down does the vector go. When you think of algebra, the slope of a line, rise over run, really this is another way of talking about slope. How far up and down, rise, how far side to side, run, is a vector point. This is another way to talk about direction, to say that instead of it being, 5 units at 30 degrees north of east, you could say something like, 4 units east and 3 units north, and get the same piece of information. Let's look at some quick tricks of how to find vector components and how to use them. The first thing we need to do is define a coordinate system. The most common coordinate system we deal with is this one here I have on the right. Is what I call the XY right-handed coordinate system, where positive x is to the right, positive y is up, negative x is to the left, and negative y is down. And here I have a vector A, and it points up and to the right. So what AX and AY are really these two dashed lines. It's worth pointing out if you add up AX and AY, the vector components end up with the original vector. If I did AX to the right, AY up, I would have done A as my sum of those two vectors. Now let's say that angle is angle theta, and let's look at how AX and AY relate to one another. It is worth pointing out that the vector components of a vector are also vectors in and of themselves. The way we would determine direction for vector components is either plus or minus. It's either going right or up, positive, or left or down, negative. Some equations that we could have: the magnitude of A is equal to AX squared plus AY squared. And we also can relate AX and AY to this angle theta. In this case, if theta is the angle with respect or between AX and A, then AX is equal to A times cosine of theta, AY is equal to A times sine of theta. So let's do a quick problem and see if we can break up a vector to its components. And so we're going to have a car that's going to travel 50 miles in a direction 30 degrees north of east. And so I drew the picture here. I have 50 miles. 30 degrees north of east means that if I started off east, I'm moving 30 degrees north of that line. That's telling me the angle between AX and the vector. We're going to find the east or x component and north or y component of this vector. What we're going to do is some right triangle trigonometry. Really what I've created here when I'm breaking this vector up into its components is a right triangle where I don't know the two sides, the AX and AY. I have AX is equal to A times cosine of theta, AY is equal to A times sine of theta, and so we can actually solve it out right away without doing any further work and get our two components. Worth pointing out that both of these are positive because this vector moves to the right and moves up. We can also take components and get a vector back out of its components. This is what I would call resolving components into their original vector. In this case, I have B and C, two vectors. I'm giving you Bx is 4, By is 3, and Cx is negative 6, and Cy is 4. The two pieces of information I need in order to resolve a vector into its components are the magnitude of the original vector and the direction of the original vector. Now to find the magnitude, I use Pythagorean's theorem. Remember that we're going to be drawing a right triangle where I have 4 on the x-axis, 4 on the x, 3 on the y. And so b squared is equal to 4 squared plus 3 squared. B squared is equal to 25, so the magnitude of b has to be 5. If I draw out what that angle looks like, and I'm going to move this out of the way for you. I'll put it up here. X4, Y3. We want to find this angle in here. Easiest way to do that, is to say tangent of theta is equal to 3 over 4, opposite over adjacent. Solve for theta by doing inverse tangent, and so it's 36.9 degrees. Now 36.9 degrees is not specific enough to specify direction, because there are at least, there's at least 4 angles, and there's probably 8 angles that I could draw with respect to a x direction or y direction that are 36.9 degrees. So I would actually define this as 36.9 degrees above the x-axis. If this is the x-axis, the angle is 36.9 degrees above it. Now you could also say 36.9 north of east as well. So vector B is 5 units at 36.9 degrees above the positive x-axis. So that is resolving this vector from its component. We can do the same thing for vector C. Vector C squared is equal to negative 6 squared plus 4 squared. So C squared is equal to 52, so C is about 7.21. If I draw this thing out, we can solve for theta. Tangent of theta is equal to 4 over 6, opposite over adjacent. Theta is equal to 33.7 degrees, and we would say that that is 33.7 degrees above the negative x-axis. One thing to point out, when I calculate the angle here, I actually drop this negative sign and think of it as, what is this angle in this triangle? And then I account for that negative sign right here when I say above the negative x-axis. That includes that information about that negative sign. So vector C is 7.21 units at 33.7 degrees above the negative x-axis. So the last thing I want to point out is what I call some direction conventions, some way of describing different directions. And there are really 8 ways that you could define a direction. You can define a direction north of east or east of north. You can define a direction south of east or east of south, south of west or west of south, north of west or west of north. Generally speaking, we normally use north of east, south of east, north of west, southwest. If we're defining our vectors the way we've defined them previously, those are the normal directions we would normally be working with. When we say north of west, what that means is you start at west and the angle goes north from west. Same thing as above the negative x-axis. If you started east of north, it means you started at east and the angle points east from north, or right at the positive x-axis. Keeping this map in your head, these conventions for direction, are actually pretty important. This is the way we define angles in physics, so we can specify, well, what 36-degree angle are we talking about? If it's 36 degrees north of east, I know that I started off in the east direction, and I moved at an angle 36 degrees north of it, so I'm moving off over here. Let's get a quick overview of vector components and breaking vectors up into their components and taking components and resolving a vector out of components.